Good morning, everyone, or good afternoon, everyone. Let me know if I'm audible, screen visible. Hello.
Yes, sir, you're audible.
Okay, thank you. So let's start today. Last lecture, we have discussed link state routing and distance vector routing. Those routing protocols, as a categorization of dynamic routing protocols, gives us the basic idea on how a routing protocol would work. Conceptually, they give good understanding, but in practice, can they really work for a large network? Consider that we have about large number of networks, let's say around millions of networks, and millions of network, each router need to store a routing table entry for those networks. If router is to store entry for those networks, number of entries would be very large. And when number of entry becomes very large, we'll have memory issues, performance issues, looking at that. Secondly, both link state routing and your distance vector routing exchange routing packets. For a link state, each link information is communicated to all other routers. So if I have millions of routers in the network, link state information from each router would go to millions of routers. And that means, so if I have a router here, and number of routers connected, and that means this information of link state has to go here, here, here. And if this is a large network, my network would be flooded with this link state messages itself and will be choked. If you are looking at distance vector routing, size of my broadcast message, because my link is distance vector routing, a router communicates entire routing table to the neighbors. So if I have a million networks, my communication to neighboring router would contain million network entries, and that packet size would be too large, and that will even choke. And each time we receive a routing message, we do computation, and that means my computation cost will become very high. So these protocols, both link state routing and distance vector routing, good from idealistic understanding perspective, understanding yes, but they cannot scale up. They cannot scale up because network is too large. Further, network is considered flat. Flat meaning each router is the same level as the others, and each router gets information to the others. And in real life, that is not the case because the internet consists of many networks, and one network would like to maintain its autonomy. How my network is shouldn't really matter to the other guy. We can look at an example. Let's say in a house, you are 6 members staying in a house. Now you like other world to know your reachability that these 6 people stay in the house, so that a letter addressed to any of you should come to your house. But whether 6 of you stay in a single hall, or each person stays in a separate room, or you have a 2 bedroom or 6 bedroom, or whatever size of house and structure is, you wouldn't like the outside world to know how good the house is, or how it is connected, how do we live inside, because this is your autonomy, independent information. And you wouldn't like your autonomy to be disturbed. You want reachability, that people can reach you, but you don't want how you're internally connected. Same way in the network, a network administrator or in charge would like to communicate with the network reachable from me, but would like to maintain the autonomy. How do I connect my routing? What routing protocol I run? Whether do I run link state or do I run the static routing or whatever, shouldn't really matter. And that means we need a different category for routing protocol, which we'll refer to as hierarchical routing. In hierarchical routing, we basically aggregate routers into regions, group them together so that this becomes one network under the control of one network administrator. So all the routers under the control of one network authority group together, and that is called autonomous system, or what we also study as AS. Now with the autonomous system, you know internally, so all routers within the autonomous system would be flat, they talk to each other, but to outside world, that means to other autonomous system, they only know reachability, they do not need to know how they're connected. So within the autonomous system, you run your intra-AS routing protocol, which could be link state, distance vector, stating, or own proprietary, does not really matter. But in different autonomous systems, you need a different protocol that communicates. The reason why intra-AS routing protocol will not work across the autonomous system is because in the intra-AS routing within the network, so this is my network. Sorry. Within my network, how I'm connected, and we always look at the link cost, we define the link cost, we know this link cost. This link cost could be 3, this link cost could be 6, this link cost could be 8. I define the way my cost is, and doesn't matter to outside world what my different networks are. We just wanted to communicate the information. And one autonomous system, let's say this one autonomous system, this is another autonomous system. So these two systems would be connected by what is called your gateway routers. So autonomous system, you run inside whatever protocol, and at the edge you connect two autonomous systems, and on this link, you communicate information that belongs to your network belonging to you, network belonging inside to you. That's what you communicate, and that's the way things work out. So look at the example here. We have three autonomous systems: autonomous system 1, autonomous system 2, and we have autonomous system 3. Now in the three autonomous systems, within the, let's say, autonomous system 3, they run any intra-AS routing protocol, and they'll indicate whatever networks are there need to know each other routers. Similarly, in this autonomous system 2, they run intra-AS routing protocol, and they would know connectivity of each network inside, and they connect. And same is true for autonomous system 1. So when you build a forwarding table of router 2B would basically entry have this network, this network, this network, this network, and you maintain, run, and you know a respective cost. So we need one routing protocol within this autonomous system that communicates what the different networks are. And this routing protocol knows somewhere the cost and topology. But all the network within this, let's say there's a network N2, now machines in this network should be able to reach this network, but without bothering about how this network is connected within this autonomous system. That means we need to have one routing protocol that runs across this autonomous system. And because you have number of network inside N1, N2, N3, and these networks need to be known, to these internal routers 1A, 1D, 1C, something of that kind. That means we also need a routing protocol that propagates reachability of network in this to this. So that is the job of Intra-AS routing, which basically needs to build reachability across the AS system and build a routing table of routers of the other networks. Now, if we look at here, in these three autonomous systems, AS2 is connected to AS1 using only one link. So is AS3 is connected only one link, but AS1 is connected to AS2 and AS3 using two links. Now let's say there is a network X here, there is a network Y here, and 1D gets a packet for a destination X. How does 1D decide? Should it go to 1B to go to AS2, or should it go to 1C to go to 3A? So question basically is, how is the routing in AS1 of forwarding table AS1 different from forwarding table of AS2 or AS3? What really makes a difference in terms of computation? Any thoughts? Anyone would like to give a thought how the two routings are different in the way they would work? Anyone?
AS1 is in the middle.
Right. So if, let's say, consider router 3B gets a packet, so let's consider we have a network X here, we have a network Y here, and we have a one network Z here. Now 3B gets a packet for destination Y or Z. What it will do? Instead to send a packet to 3A, it knows there's only one way to go out, and 3A will take care of it. So as far as routing table is concerned of 3B, 3C, 3A, for all the other networks outside AS, they know my gateway is 3A. There's only one single gateway, that's the way it works. Same way, any router in this AS2, when it gets a packet for your network X here and network Z here, it knows that packet has to go to 2A, and 2A will give to and goes out. Doesn't matter whether packet is for X or packet is for Z, it always go via single. But can the same thing be said about routers in AS2? You have, let's say, network X here, and you have a network Y here. Now, when 1D gets a packet for destination X, can it send to 1B? Can it randomly send to 1B or 1C? But does it need to differentiate that X means it has to go to 1C and Y means it has to go to 1B? It needs to differentiate. Because for X, 1D need to send a packet to 1C. For network Y, 1D has to send a packet to 1B. And that means the job of determining which is my next gateway for a given network, it becomes complicated when there are two AS systems connected to my AS. Let's look at with a better example in the next diagram. Consider that the router in AS1 receives datagram outside of AS2. Now this router receives a packet. Should it go to 1C? Should it go to 1B? It needs to know from which is the connecting gateway, and that is what it must need to do. So router 1D must know that which are the networks reachable through AS2, and only for those networks, packets should go to 1B. And for all the networks which are in AS3 or network connected via AS3, packets should go to 1C. That means 1D should know about not only the external networks, but it also need to know external network is which is my best next hop. It need to get that information, and that's the job it must to do. And that means when we propagate reachability of network of the other autonomous system to within the AS1, they also need to know which is my best gateway, which is my nearest gateway. And that's the job required done. And this is done by Intra-AS routing, because if I'm running Intra-AS routing talks about networks within the autonomous system. Intra-AS routing does not deal with network outside the system because we represent this whole network as a graph. And if you were to include other networks, we need to know their cost. Whole network becomes simple and scaling becomes an issue. So intra-AS routing provides the routing table, forwarding table, only the network within the autonomous system. But for network which are outside the autonomous system, we need to run inter-AS routing, and that's the job of inter-AS routing that we need to do. So let's do an example here. Consider a network X, network Consider that network X is reachable via AS3, and that means when this information reaches to AS1, AS1 knows that 2X packet has to go via 1C. So all the routers gets to know for network X, send a packet to 1C, which will take care, go to 3A, and packet will go out. And that means the router 1D will look at the interface, it has number of interfaces, look at which interface I need to use to send a packet to 1C, and in its routing table, it will make a destination X, and interface out is L, which is connected to 1C, which is the gateway. And this information has to learn from inter-AS routing protocol. If X is reachable, as in this case, via only one AS, which is AS3 is fine. What happens when, let's say, X is reachable via two networks? That means X could be reached via AS3, X could be reached via AS2, can be reached via both. And now when 1D gets the information, it knows that X can be reached via gateway 1C to AS3, X can be reached via gateway 1B through AS2. So which one I should be using to send a packet? And that primary job is their job is run by what is called hot potato routing. And hot potato routing means that 1D knows X can be reachable via 1C, X can be reached via 1B. Now it knows the cost of 1C, it also knows the cost of 1B, and it determines which is nearer to me. 1D determines the cost to 1C, cost to 1B, and whichever has a lower cost, it will send the packet to that. It may so happen that, let's say, it chooses 1C to send it to X because 1C is nearer. So let's assume the cost from 1D to 1C is 2 and cost from 1D to 1B is 5. Now because 1C cost is lower, 2 packet X, it will send via this and packet will go. It doesn't really care what the other costs are. Consider that this cost is 100 and this cost is, let's say, 20. And this cost is, now this is 2 and this is 5. And so this link cost is 10 and this link cost is 10. So using hot potato routing, 1D will still send a packet to 1C because 2 is closer. But if you look at the overall cost, it becomes 2 plus 10 plus 100, which it becomes 112. Whereas on this path, it becomes 5 plus 10 plus 20, which is 35. So overall cost, this path would be cheaper and better, and this path is longer, takes more cost. But hot potato routing means a router 1D chooses which is nearest to me rather than the overall cost. It's something like you want to go out of the college and ask somebody, and you want to get, so you're directed, go to the nearest exit gate. Doesn't matter that if you were to go out via, let's say, back gate, it may be cheaper for you to go to Coffee Hut, but rather than going the main gate, you may walk longer. But depending on where you are, the college security says get out of the main gate even though it takes you longer because they want you to vacate the college as soon as possible. And that's the concept of hot potato routing, and that is what we use. We look at that. So generally, how does a router using inter-AS routing build the forwarding table? Using inter-AS routing, it learns network access is reachable via multiple gateways. Like the router 1D understands it can be reached via 1B and 1C. Once it knows that network X is reachable via multiple gateways, then it using the intra-AS routing, because intra-AS routing has told it the cost of 1C and 1B. So for all the gateways, you got using intra-AS routing, you determine the cost of all the gateways. Once you know the cost, you determine which gateway is closest or which gateway has the smallest cost. Once you identify the smallest cost gateway in your forwarding table, you basically make that entry for the least cost gateway, and entry would be destination X using interface L, the interface that leads you to the least cost gateway, and that basically concept of output auto routing. So this is what we basically looked at, the job of inter-AS. Now we said AS is aggregation of different routers in a network. Does that mean that one ISP which controls one network has only one AS? If ISP is big enough, ISP may break their network into multiple ASs and not necessarily one AS. But one AS will belong to one authority, one AS would not belong to multiple authority, but one ISP can have multiple AS, it can break and decide accordingly. And with this grouping of routers into one AS, we get the capability of scale. That means we can have more networks, we can add things, and we always add with a prefix. And network also has an autonomy. You don't have to convey how your internal structure is, how you are connected, what internal costs are. You only communicate reachability. The example I gave of the house. So with AS, we get a benefit of scale and autonomy. Certain constraints within an AS, a router has to run same intra-AS routing protocol. Within an AS, you cannot say one router would run link state and other would run distance vector. But two different AS systems can run their own different routing protocol. There is no constraint that all ASs should run same protocol. No, they can run different AS routing protocol. And we'll look at also, when you talk about inter-AS routing, we look at policy support that we look at when you deal with BGP kind of protocol. So what does intra-AS routing implementations are? Intra-AS routing means routing protocol running within a network. And since they're running within an autonomous system, these are also called interior gateway protocol because they're running protocols within the network. And the two most common protocols are, one is called RIP, Routing Information Protocol, other is called OSPF, Open Shortest Path First. RIP was the first protocol that came in, you can say RFC 1058. RIP has a limitation that it did not support classless networks. That means it supported only network with a subnet of /8, /16, and /24. It did not support classless, that means I can have subnet mask of 10 or subnet mask of let's say 24 or subnet mask of /30. It supported only fixed classful networks, whereas RIP2 supported classless, that means you could have any network sizes. RIP has other limitations. It does not support multiple paths for the same destination. There is no service-based or quality-based routing. It's a fixed routing, and we look at shortly. OSPF, currently we basically run version 3. It has more secure features. There are other interior gateway protocols. One is called IGRP, Interior Gateway Routing Protocol. It is developed and designed by Cisco. It is under link state routing, but proprietary to Cisco. And that basically means if your whole network consists of Cisco routers, then you can run it. But the challenge is, if you have running IGRP, you cannot buy any other router. You are logged into Cisco routing, so which may not be a desirable situation for you. Let's understand how does RIP protocol works. RIP, a routing information protocol, was first available as part of USD BSD Unix, which is Berkeley System Unix 4.2 as part of first TCP/IP implementation. So first TCP/IP stack was available in BSD Unix. If you look at Windows 95, it is the first Windows that has a built-in network support. Windows 3.1 before that has no networking support and to run separate networking stack. Now, the RIP protocol, because it's available by default in Linux, it became more widespread and people adopted it. So RIP is basically distance vector routing, and the way RIP works is it assumes all the link costs are same. So that means link costs are all one. The RIP protocol only looks at number of links for a destination. It does not really look at the edge cost. For it, all the edges have same cost. It looks at only length of the link and not the edge cost. That's the limitation with distance vector routing, and that means each link has cost one. Further, it works with a small network. That means router 1 to other router, if it is more than 15 hops away, that's the maximum it can support. So any router which is more than 15 hops away, it will still keep hop count as 15, link path is 16. It will not do more than that, and that's another limitation with RIP protocol. And as part of routing exchange, A would send its routing information to B would send to A, to D, and they do periodically every 30 seconds. Now, because network could be little large, and if I have, let's say, 100 networks within my entire AS, now if A communicates that all the 100 networks single message may become too big. So for convenience, no routing message contains more than 25 destination subnets. So that message size could be limited, and that means if you have 100 networks, we're probably sending four messages. So just look at how does my RIP table look like. Consider the router A. We have different networks U, V, W, X. So A is directly connected, directly one link. So I would say A to U, hop count is 1 because we're directly in one link. U to A to B, so A to V, we have one link here, one link here. So hop count to V is 2. Similarly, hop count to W is 2, 1, and one link here. Hop count to X and Y would be 3 because 1, 1, and one link here and one link here. So both X and Y, my hop count would be 3. What would be my hop count for Z? Will it be 4? 1, 2, 3, 4, or will it be something else? Any questions, any comments? What would be my hop count from A to network Z? Will it be 4? Will it be something else? Any questions or any comment? Anyone? Vidyasri?
Sir, is it 2?
Yes, it is 2.
I don't know.
Because A to C is one link and C to Z is another link. And that's the way RIP really works. Let's look at another example, how the RIP updates. Consider this network. So I'll look at the routing table of router D. You can look at X is 1 hop away, W is 2 hop away, C is 2 hop away, and consider that you have some links, Z is 7 hops away. Assuming this is what your routing table is. And now a router A sends its own advertisement to D, because as part of distance vector routing, each router sends to its neighbors its own distance vector. Now A sends, W is 1 hop away, X is 1 hop away, C is 1 hop away, and Z, somehow it knows that Z is reachable with a distance of 4. And that is what it communicates to D. Now when D gets this message, D looks at that my cost was 7, but via A, I have 1 hop to A, and A to Z is hop of 4. That means if I were to go to network Z, my overall cost would be 5, and hence D updates its hop count to 5, and next node becomes A. Previously it was B. So previously to Z network it was B, but once A sends a routing messages, the next hop becomes A, and that's how things would happen. And that is how the RIP protocol works. RIP has a limitation of what we call count to infinity. So look at the following. Now table is made. Now this link goes down. When this link goes down, A would make the cost to infinity. Immediately when this happens, D sends its routing message to A. And this is the routing message D would send to A. It says, look, and when they communicate the message, they only give destination subnet and the hop count. They do not send what the next router is. When you communicate the message, you only give destination subnet and the hops. So with that, when D communicates to A that I can reach W with a cost of 2. Now A thinks W is down, and this cost has become infinity because my link is down, but A receives that D is saying W can reach the cost of 2 and A to D is cost of 1. That means A can reach W via D with a cost of 3. And thus A updates its hop count to 3. Now because it is updated, A will send this information back to D. When A sends to D, D has previously learned from A that distance was 1, and now A is sending my distance is 3. So remember, it looks at the link cost A and reachability of A is to 2. So that means the A is saying to W, my cost is 3, and D to A is 1. So D would update this entry to W as 4. It will communicate back again. Now D is saying to A, my cost is 4, and A to D is 1, so A would update this cost to 5. And that way they keep on increasing, this becomes 6, and this is called count to infinity problem. How long you keep on increasing, and to avoid keep increasing forever, the max hop count was limited to 16. And that's the reason, and this problem is basically count to infinity. The solution is what is called Poisson reverse. Poisson reverse meaning D should not send information about W to A because D has learned about W only from A. Now D has learned about W only from A, then D shouldn't be updating A. To be consistent, what D does is when D sends this routing information, look, this is the information. When D sends this information to B, it will say W is reachable with a cost of 2. But when D sends the routing information to A, it will make this value as infinity so that A does not wrongly update cost to W because the link is down. So basically means when D is sending a packet to A, it is poisoning the route to W with a poison of infinity cost. And because I am corrupting the entry deliberately, called poisoning, so that A does not make a wrong entry and we avoid count to infinity problem. And this is what is called Poisson reverse, which is used to avoid count to infinity problem. So RIP has limitations, we send the limitations, but if link failure occurs as we've seen, we can basically goes into what is called count to infinity problem, and to avoid that, we do Poisson reverse. Basically means we do not communicate information about a network to a router from where we learned. Is for example, if I learned something, let's say I learned database from some person X, then I shouldn't be teaching back the same person X this the database. I can teach others, but not to the same person I studied. And that basically is Poisson reverse, and this is always to avoid your count to infinity. RIP1 we said has a class full routing. RIP2 has classless routing, stands for classless inter-domain routing, and that means when you communicate the network, you also communicate net mask. which could be anything from /8, /9, /10 up to /30. And it supports aggregation, multiple routers could be combined. Now RIP is implemented via daemon called route D. Route is application process that runs. It runs on transport layer, which makes use of UDP, which runs on top of IP. So RIP is run by application called route D, which makes use of UDP and then the IP. Whereas OSPF runs on top of IP, OSPF does not use transport layer. And this is the communication diagram, the way RIP implemented, and this diagram is taken from your book, which is figure 4, number 39. To avoid the limitations of RIP, like I have a count infinity problem, we have this, we cannot use the multiple paths, single destination, we cannot differentiate between type of service. So new protocol suggested called OSPF, open shortest path first. That basically means protocol is open. That means anyone can implement. And RIP does no security. One could send malicious message and corrupt routing table of others. So OSPF implements some malicious mechanism. One mechanism called simple password communication, other is MD5 based. This is actually not a security feature, it is misnomer, because in the routing message, we send password in clear text. And all that the receiving router do is check, is this password same as password stored with me? And if it is same, it will consider routing information is trustworthy and update the routing table. And if password value does not match what is stored, it will discard. But that means I'm broadcasting my password. That means a malicious router could receive this information, store the password, and then use same password to corrupt other routers. So it is more of an identification to just trust whether information is right or wrong, but not a security feature. Actually, one uses MD5, and the way the MD5 communication works, I have a routing message. So let's say this is my routing message, contains all the networks and the hop. To this routing message, I append my what is called shared secret. To this routing message, we append what is called shared secret. And for the whole message, we run MD5 algorithm and generates MD5 sum. We generate MD5 hash. And when the message is communicated the routing information plus MD5 sum. The shared secret is not sending any messages. What is communicated is routing network details plus MD5 hash. Receiving router receives this information. It also appends its own shared secret, compute the MD5 sum, and compare this MD5 sum with the received one. And if the two matches, then it knows it's from a genuine router, or otherwise it discards. Because this shared secret is configured in each router separately, and the shared secret is not communicated at all, so that means a malicious router or attackful router can connect to the network, but because it will not know the shared secret, so it cannot poison or it cannot corrupt the routing table. And in that true sense, using MD5 sum based basically is a true security feature that we can avoid poisoning the routes and creating bad entry. OSPF also supports what is called same cost multipath. Let's say this is my router R1, and I have a one path and I have a two path to go to some network. So this is network X. Two network X, cost on path 1 and cost on path 2 are same. When the two costs are same, RIP would use only one route and not both. And that means all the packets will follow only one route, and this link or this path will be empty, and we are underutilizing the network. So for that purpose, we would like to say when both the paths have the same cost, I should be able to load balance, send one packet there, and another packet. So send one packet on one path, send another packet on another path. we can do load balance and use both the links. So OSPF supports multiple path, equal cost, multipath routing, also known as ECMP. Its term is ECMP, equal cost multipath routing. That means for a given destination, if there are multiple about the same cost, then traffic can be sent, there will be multiple routing entries, and packet could be load balanced across the different paths. Further, OSPF also supports what is called type of surface-based routing. Consider satellite link. Geostationary satellite are at a distance of 36,000 kilometers, and considering the speed of light in vacuum is 3 into 10 raised to power 5 kilometers. On one link, time taken would be 120 milliseconds. And since if I'm communicating via satellite and there is a satellite here, so packet has to go this way and come back. So one hop will take me at least 240 milliseconds. And the distance of 36,000 kilometers is taken from equator. From other parts of the earth, it is more. So typically this distance is taken little more. So rather than this 240, it may become little more. So it typically becomes 270 milliseconds we take about taking the average. And that means if I use satellite link to send a packet, it will take about 270 milliseconds. Now this delay is way too high for real-time voice communication, because for voice, we expect delay to be less than 100 milliseconds, and this takes already more than 200 milliseconds. So that means we wouldn't want any satellite link to be used for voice traffic, a real-time voice traffic, but for data traffic, this link is great because it's high bandwidth. So we'd like our routing protocol to differentiate the kind of traffic we are sending, or what is called as type of service. So if you have the satellite link, it will have two costs. One cost for best of all data traffic, one cost for real-time traffic, for example, voice traffic. And that means I can send different packets on different routes. And that support is also given by OSPF, and that's how it works. Another feature OSPF support is supporting multicast and RIP uses broadcast. And when study multicast routing, in about 1 or 2 lectures later, we'll look at how does multicast works. And of course, OSPF hierarchical. The way we started with hierarchical routing, that's the way OSPF works. So basically, OSPF introduced the concept of area. So you have one called backbone area. And then other areas can be defined as many as you want. Area 1, Area 2, Area 3. And because the different areas, you have a different nomenclature. We have one is backbone router. Job of backbone router is to communicate routing information within the entire backbone. This whole thing represents one autonomous system. So this would be connected to another autonomous system, and that's the job of boundary router. So boundary router connects one autonomous system to another autonomous system. So boundary router, one autonomous system to another autonomous system, and there they run Intra-AS routing protocol. Now these areas, they run their own link state routing protocol, and topology is visible only within this area. Then you have border router, area border router. Job of area border router is to get routing information within the area to the backbone. So each area talks only to the backbone. Each area talks to the backbone. The two area does not talk to each other directly. Two areas do not talk to each other. They always talk via the backbone. And we have the what is called internal routers. Job of internal router is to communicate reachability within the, so nomenclature wise, OSPF we define two level hierarchy. One is called backbone area, and then the other areas, and all the area they run linkage advertisement, and within an area they are the entire area topology, because the linkage routing does give you that. And for other areas, they only know the shortest path. They don't know the whole topology, and they try to hide. So within an area, we can basically, we are doing achieve of scaling because we are not communicating entire network. We only know reachability part, and that's the job OSPF does. Area border routers communicates with backbone routers to the areas and get the basically information of the networks about the area. Backbone router, as we said, OSPF routing within the backbone, and boundary routers connect to the other autonomous systems. Now, area is represented by a 32-bit integer written in DDN4, which is called dotted decimal notation. That means we write the area number as like an IP address. Backbone area is always called area 0 and represented with 0000 or 0.0.0.0. Other areas could be by like IP address representation, some number written in the form of A.B.C.D. And job of backbone area is to distribute routing information to the other areas. Each area has to be connected to the backbone area. If it is not directly connected physically, it may connect via other areas, but logically, you basically set up using virtual links. But two areas, even though may be connected physically, they don't talk to each other. Each other area talk to only the backbone area. Just comparing the OSPF versus RIP. OSPF basically can calculate separate routes for multiple paths with the same distance. It can have a different route based on the different type of traffic. For example, real-time traffic versus data traffic. For the same destination, we can have different routes. We can have multiple routes for same destination, same cost. That means I can do load balancing of traffic. In OSPF, which is link state routing, each link is assigned a cost, which is a dimensionless, something called a metric number, which is typically a combination of inverse of bandwidth, delay, reliability. In RIP protocol, there is no link cost. You always take link cost as one fixed, and you only count number of links, basically number of hops. And because of equal cost, it supports load balancing. OSPF supports subnet. That means it supports classless network, so network could have any mask. Another benefit is if you are doing a, let's say, leased line link or virtual connectivity link, let's say through microwave or leased line, then point-to-point link, you do not need to assign IP addresses. In RIP, even if the network has two hosts, you still need the network addresses. That means the point-to-point link is the only use for traffic. We don't need to waste our network addresses, so we can save that as another gives you. And lastly, the OSPF supports authentication, and in that sense, no malicious router or a bad router can come into the network and create bad routing information across the network. So using MD5 it prevents primitive level, it does simple password communication, which is more for identification, whether it belong to this network or not, to avoid misconfiguration, but not really a security feature. And RIP runs using UDP. So RIP is a routing daemon which runs on top of UDP, then IP, where OSPF run directly on top of IP. It does not need any transport protocol. OSPF is a link state protocol, and hence it does fast convergence. Then the RIP, which has a slow convergence, and there are no count to infinity problems with OSPF. What these protocols, the intra-AS routing, like OSPF, RIP, or anything, not do is support policy. So we'll look at policy support in our next lecture. Example of policy would be, let's say when Indian PM has to go to Afghanistan, it will not fly over Pakistan, it will take a roundabout route, which is longer, takes more time, but more fuel, but security perspective may be fine. So if you want to go somewhere, you have two paths available, but one path you have a risk. There may be some element there, antisocial elements. Your life could be at risk, or there may some kind of inconvenience. So you take a longer route, takes more time, more money. So you can define policies and decide which way my routing has to go to, and that policy support is not available in intra-domain routing or intra-AS routing, and that is what we'll study in our next lecture when we study inter-AS routing or called BGP protocol. With that, we come to the end of the lecture.